All right, let's take a look at 11B, check your understanding. Some vocab again at the top here. The y-intercept of an exponential graph is also called the initial value. If an exponential graph goes up as you move from left to right, then we say it represents exponential growth. Which makes a lot of sense. If an exponential graph, however, goes down as you move from left to right, then we say that it represents exponential decay. Okay. Not as commonly used word as growth, but that's what we've got going on. Okay, on Google Classroom, there's a link to a Desmos calculator document with an exponential function represented as f of x equals a times b to the x. Okay, I'm going to do the version on my phone because I wasn't techy enough to figure out how to do that from my camera here on the computer. So, what does the number a change in the graph? So what I'm going to do is I'm going to grab the a and I'm going to slide the a value around. I'm going to move the b a little bit here first as well. As I slide the a around, it looks like there when the a is -1, this graph crosses the graph at -1. When a is -2, this graph crosses the graph crosses the y-axis at -2. When I make the a 3, I get it crossing the y-axis at 3. So it looks like what the number a does is what does the number a change in the graph? It changes the y-intercept. It looked like it was doing some other kind of bizarre things as I moved that around there. It certainly whips that part around there a little bit when the a's are negatives. We don't often have negative values of a, but it kind of looks like the whole graph is, it's peeling it away from the positive x-axis, or it's pushing it down toward the positive x-axis, but it really does that via the y-intercept. Okay. A comma or 0 comma a is the y-intercept. Okay, what does the number b, usually called the base, change in the graph? So if I bring this in here and I start moving the b around, I get a switch there between, that's exponential decay, that's going down as I go from left to right, that's exponential growth. If I look at the actual values of b, which don't show up in this very well with the glare, but if you were doing that, we would see that these values of b for decay are numbers like 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. 1 is just flat, it's not exponential at all. And then when I get bigger than 1, I get exponential growth and it starts to get really steep. Okay. So closer I get to 0, the steeper it decays. The bigger I get past 1, the faster it grows. So b values that are between 0 and 1 make decay, and b values that are bigger than 1 make growth. Okay. And the bigger these things are, the faster the growth. Closer these are to 0, the faster the decay. Okay, so armed with that information, if I'm going to match graphs to equations 3 times 1.5 to the x, here's that initial value, there's my A is 3, and this is the only graph that crosses at 3, so this must be the y equals 3 times 1.5 to the x. Because of that, and because it's growth, that number was bigger than 1. This one, 1/2, this is definitely a decay problem, so it's one of these two, and the initial value is 1.5. That's happening right there, so this must be the y equals 1.5 times 1/2 to the x. 0.7 is smaller than 1. This graph crosses at 2, so decay crossing at 2. This has to be the y equals 2 times 0.7 to the x, which leaves growth here crossing at 1/2. So this one is the g of x equals 1/2 times 2 to the x. I guess this said f of x, not y, so we'll make that an f of x. Okay, so kind of highlighted on the other side, to represent exponential decay, the thing that controlled that was the b, and b values between 0 and 1 made exponential decay, but if the b value was bigger than 1, then the graph represented exponential growth. So if I look at these, here's my b, this is bigger than 1, so this is definitely growth. My b here is 3.1, that's bigger than 1, so that's growth. 0.79 is smaller than 1, that is decay, and 7/8 is smaller than 1, so that's decay. Doesn't matter what the a is when I'm determining whether it's growth or decay. Okay, in a geometric sequence we found a common ratio in an exponential equation that represents the sequence. We call that number the growth factor. That's the thing that we multiply by over and over. What we refer to as the initial value of an exponential function is just the first term, or actually maybe more accurate, the 0 term in our geometric sequence. Okay, the following tables represent exponential functions because their y values are a geometric sequence. Write the symbolic form of the exponential function and complete each table. Okay, so if this is geometric, let me bring my calculator in so that I can do the 42 divided by 35, which gives me a 1.2. So my 0 term is 35, that's my a. So this should look like y equals 35. The growth factor was 1.2 to the x. And so if I want to find the 8th term in there, then I'm going to do 35 times 1.2, and I will raise that to the 8th power and get 150.5 approximately. Okay. On this one, 38.4 divided by 48 is a 0.8. So this is an exponential decay with a growth factor of 0.8. And a 0 term of 48, so 48 times 0.8 to the x. And if I want to find the 10th term, I'm going to do 48 times 0.8 and raise that to the 10th power. It's going to give me about 5.15396. I don't know why I left so much room there and not up there, but there you go. This one, don't know the 0 term, but I can still do the 3.4875 and divide by 4.65, and that tells me that I'm multiplying by 0.75, which means if I go multiply by 0.75 that way, then going this way must involve dividing by 0.75. So 4.65 divided by 0.75 starts me out at a 6.2. So this should look like y equals 6.2 times 0.75 to the x. And if that x is supposed to be a -2, then that's 6.2 times 0.75 raised to the -2 power. Gives me about 11.02 repeating. Okay. On this one, looks like what I've got happening here, I can tell from this that I'm multiplying by 2. So this must have been a 2. Okay. And my equation looks like y equals 1 times 2 to the x. I don't need to write the 1 times there because I'm a properly lazy mathematician. And 2 to the 12th power is 4,096. So that is what that one looks like.